Any questions? Okay. So, did any of you ever do the experiment of, you got a glass jar, metal top, put it under hot water to expand it to make it easier to get the top off? Got one. So, as you heat up, do an incredible drawing here of atoms inside a piece of metal. That's just a zoom in. I've got, if I have just some piece of metal right here, I'm just going to zoom in. I've got a bunch of particles that are sitting really close to each other, a little bit of vibration, not a whole lot. As I heat it up, what are those particles going to do? Okay, I saw two people with hand gestures. They will start moving more, and they'll start to spread apart some. Now, they are not moving so fast as to change it from to melt it, but they are moving fast enough to just try to get away from each other a little bit more. And so from this, we have, if you heat up a material, it will expand. If you cool it down, it will shrink. So the question I'm going to ask you is, if I wanted to find the change in length, upon what will it depend? Just based upon your gut feeling. And then I'll explain why I'm asking you this question as opposed to just telling you.
Depends on the matter, the state of matter.
The what?
State of matter that the object's in.
Okay. So it would be different for liquids than it is for solids?
Yeah.
All right. I'll buy it.
Would it depend on the melting point?
I think that would go under state of matter, that it can change. Let's assume, for the sake of this, that it's going to stay in the same state of matter. We're not going to melt it.
Would it depend on how fast the particles are moving and how far apart they spread apart, I guess?
What would that be related to more directly? The temperature. So I'll buy it, Johanny. Just temperature, I think, is a little bit more concise on that.
Does it matter the kind of material it is?
The material itself.
Yes.
Yep. Now, the material itself, combined with state of matter, because it could change depending upon what the material is in the state of matter, is bundled up in an experimental coefficient, that alpha. So that is sort of these two combined. Then we'll just leave it right there. There's more things here, but we're talking about the change in length. So if I have a metal bar sitting in front of me and it's room temperature, 28 degrees Celsius, what does that tell me about the change in length? temperature by itself is not enough. Yeah, change in temperature. And there's one more missing piece. Now I put a gap there because that's traditionally where it goes, but it doesn't have to go there. And I'll throw in, now let's give people a little bit more time here to figure out what that missing piece is before I reveal. Yeah, I'll bite it. And when dealing with change in length, we're talking about a one-dimensional change of just length. So the initial length. We'll just put L sub 0. Now, the reason why I ask it this way is I had a summer job interview when I was in college, and he asked me this question. And I did what I should never do, but I do too often, is I relied on memory as opposed to thinking. And I remembered alpha, I remembered the change in temperature, I could not think of the original length. I did not get that summer job. All right, so that alpha, of course, has its own name. It is material specific, and it's called the expansion coefficient. I guess linear expansion coefficient. Now things will expand in all three directions. If I have I have some piece of material right here, which is basically a rectangular solid or box shape, whatever you want to call it. It will expand in all three directions. However, we're just concerned right now with just change in one dimension. So we're thinking of some object that's long enough so that any changes in the other direction are insignificant. Let us take aluminum. The expansion coefficient for aluminum is 24 times 10 to the -6th per degree Celsius. There are no units on the top. And let's see, I have a 50-gram bar of aluminum. 50-gram bar. And what other information do I want to give you? It's the initial temperature is 20 degrees Celsius. And someone had more information than that there. And it's 2 millimeters by 3 millimeters by something like that. There's a couple birds on this one. So if this was a multi-step problem, the first thing is, what is the length? Well, I've given you the mass of it, and I need to somehow connect it to the dimensions. What do we have that will tell us this? That will connect mass to volume?
Weight. The weight.
Is it the weight?
Yeah.
How does that connect us to volume?
I don't know.
We could find the weight. Not necessarily in this particular case. This is something that we talked about when we hit chapters 11 through 14. What relates mass and volume? I feel like someone in here knows it, just is afraid to say it. Luz doesn't even know the question, and she's gonna tell us the answer. She's gonna deny you. What relates mass and volume?
Density.
Yes. Density. Density is mass divided by the volume. Well, our density of aluminum is 2,700 kilograms per cubic meter. And that's gonna be equal to my mass there. Well, since I'm in kilograms per cubic meter, let's go ahead and convert that into kilograms. 0.05 kilograms over the volume. It's supposed to be a V. Our math equation is this is the math problem, 2,700 equals 0.05 over. That's the math problem. So what is the volume? For those who don't have calculators, just board out how you would actually solve it.
You do 0.05 divided by 2,700.
Yes.
And the answer I got was 1.8519
E to the negative what?
fifth.
Fifth?
Mhm.
Alright, so 1.8519 times 10 to the negative fifth units.
Cubic meters.
Cubic meters. Alright, so we know the volume. It's not a very big number. If you don't like the scientific notation, you can always just do the 0.123418519. That also works. It depends upon your mood at the moment. I know the volume, I know two of the dimensions. If I've got a block, sort of a squared off block, how do I find volume?
Length, width, height.
Yeah. So I know that volume's gotta be the length times the width times the height. Length, width, height. And I don't know the length. My width, well, it's either 2 millimeters or 3 millimeters. 0.002 times 0.003. And that's going to be equal to 1.8519 times 10 to the negative fifth. That's cubic meters. That's meters. That's meters. So now we just solve for L. Somewhere around 3. It's a
Yeah, it goes 887
8.7
or 865.
units.
Meters.
Yeah. So I have this bar that is over 3 meters long. So, well, basically from the floor to the ceiling. It's really, really thin. And so I started out at 20 degrees Celsius. This is the length. I increased the temperature to 60 degrees Celsius, still well below the melting point. And the question is, how much does it expand? Now we're going to be using this equation. So my change in length is equal to that linear expansion coefficient, which you just look it up. That's 24 times 10 to the negative 6th per degree Celsius, times my initial length, 3.0865 meters, times the change in temperature. I think I said taking it from 20 degrees Celsius to 60 degrees Celsius. So my change in temperature, 40 degrees Celsius. Then we let the calculator do its magic with the slide rule or the abacus or whatever you happen to be using, your fingers, toes. So 0.0028. 0.0029. Units. Yeah. So it's going to expand. So if I have this bar of aluminum that goes basically from the floor to the ceiling, and I crank that temperature up from 20 degrees Celsius to 60 degrees Celsius, in essence, from something that's room temperature to something that's too hot to touch, it will expand 2.9 millimeters. It's not a huge expansion, but it's enough to have to be taken into account. So when you go over bridges, they often will have, especially when you're getting onto the bridge, something like that, where you've got these interlocking pieces with a gap in it so that in the summertime when it gets hot and cars are going over it, that it'll expand and it's got room to expand. What would happen if you don't have that room to expand? Thank you. If they did not build that into it, and it was just one solid piece, what would happen when it got hot?
Break.
Pardon?
Break.
Yeah, I think, KB, your hand gesture?
They were like bend.
Yeah, I think buckling is the term that I generally hear with that. It'll buckle. Sidewalks also have the cracks in them in order to, one, put your mom's back at risk, but also allow for some expansion. I assume that's still a thing. Okay.
Is that the same for tile? Is that why they put space between tiles?
I assumed that was for, it could be. I don't know how much the temperature changes inside the house, which I guess you could have tile outside.
But they, I mean, usually the tiles in the bathroom or kitchen.
Yeah.
And I would think the temperature would change.
They have grout.
I mean, the temperature would change, I'll agree with that, but does it change significantly? I don't know. I assumed it was just because if you're dealing with pieces of tile this big, it'd be a lot harder to install. But, anyone doesn't have tile lining experience? Do you notice it, it matter of temperature or ease of?
Yes, it's just a matter of ease. It's a
So-
matter of ease.
Ease?
Yeah.
Okay. In the absence of other information, I will repeat that. All right, questions on expansion? All right, let's now get down to cooling. Suppose I took this aluminum bar starting at 60 degrees Celsius and I took it down to 20 degrees Celsius. what would be the change in length?
Negative that.
Yes, negative that. Because the only thing that's gonna change, if I took the temperature from 60 to 20, if you recall, change is final minus initial. So this would become negative 40, which means the length becomes negative. And it would just shrink back to the original size in our nice ideal world. However, what I really want to talk about more is Newton's law of cooling. In the example that we did last week, we took a hot metal block, stuck it in some water, and the temperature of the water went up, and the temperature of the block cooled off, and they reached an equilibrium temperature. We went through a calculation on that. But if I took a hot block and I put it in the middle of this room, the room, for the most part, any energy that's given off is going to get spread throughout. We probably wouldn't notice. If I put a block that's at 100 degrees Celsius in the table right there, Liv, Yvette might feel it, and that might be it. I don't think anyone else would feel that sudden increase in temperature. And that's even iffy whether they would feel it. So we got a slightly different rule if I put something into an environment that's large enough so that we don't notice the temperature change in the larger environment. And I introduced Newton's law of cooling. There's a problem in the textbook dealing with Newton's law of cooling, which I've seen many students work over the years. And unfortunately, the problem that they give, you can get the right answer doing it completely wrong because of the numbers that Hewitt chose. So I'm going to go through an example, which are not using those numbers, so that there's a little less, so you can't really accidentally come up with the right answer.